as revision for test number 3. I will reiterate one more time for a few of you who are on record as saying, I've just watched the video. Don't just watch the video and think you know everything. It doesn't include everything in the test, and it sure as heck doesn't mean you know it. So use this video, hit pause, get your textbooks out, and revise at the same time. So let's go. So everything is made of plus and negative charges. Plus is called protons, negative is called electrons. If you take an insulator, and it's got to be an insulator, can't be a metal. The electrons flow on and off a metal too easy. Got to be an insulator. If you rub them, you're able to transport these little negative electrons. If we look at an example of induced charge, we can take something like a balloon, and if we bring in a charged balloon, for example, it's positive, it's lost its electrons to somebody's hair, then what we're going to do is we are going to attract all the electrons in the wall. The total charge of the wall remains the same, in this case neutral. However, you are going to create this localized field, and that's going to cause attraction. So this is how you can take something neutral and still attract it with something, in this case, positive. So that's induced charge. Possibilities of dangers, particularly lightning. As rain falls through the cloud, it carries away the charges, so down go the minuses, leaves the bottom of the cloud positive. As that difference in charge builds up, a lightning bolt passes down, and that is the discharge of lightning. The reason that the electrons move is all down to the size of them. If we look at one and we do mass, if we look at the proton, we call that an atomic mass of 1. However, if we look at an electron, it's a mass of 1/2000th, give or take a little bit. And so it's for this reason, plus the fact they're in the outer shell of the atom, that means they can be moved on and off and are free to move. So that's the very basics of static. Next, test circuits. In a test circuit, and here I have 3 devices, a fixed resistor, a diode, and a light bulb. We can put these devices into my test circuit, and we need to measure both the current there and the voltage here with a voltmeter. Pay particular attention to the ways you plug them in. You've done this in year 8, I think in year 10, and now again in year 11. Make sure you know this circuit. So if we mess about with the voltage, we turn the voltage up and down, we change the amount of push acting, we see for a fixed resistor it's a linear graph. As you increase the voltage, you increase the current in a proportional way. You'll notice all these 3 graphs have the minus part on them as well. That's because if we turn the plus and the minus round on the power pack, we get exactly the same numbers, but we get the negative versions. And if you do it correctly, you should get a line of best fit straight through the middle. Other ones, if we take a light bulb, we find that a little push causes a big change, and then the amount of increase decreases. We end up with this shape, this curve, through the origin again, and again mirror image, like so. And if we take a diode, we find that it has very little resistance, but if you try and run it the wrong way, you get nothing. So it's effectively a turnstile for electrons. But I'm particularly interested in is what's going on along here. If we take my fixed resistor, at all points the gradient of this line is constant. If we were to put in another resistor, say this was 30 ohms, if we were to put in a 15 ohms, it would be steeper. So from this we can tell the steeper the gradient, the lower the resistance. It's kind of counterintuitive. So if we now take this and we look at my light bulb, we can see the first bit has a steep gradient, so we can say it has a low resistance. And then as you increase the velocity, the voltage, got V's on the mind, the gradient is slowly decreasing to the point where you have no increase at all. At this point you've reached, almost like terminal velocity, you've reached a terminal resistance. And at that point, you're just waiting then for the light bulb to snap. Next, we've got two other types of resistor. This one, the arrows represent light, so this one is an LDR. And this one with a little golf club through it is a thermistor. This is the thing that's responsible for knowing when to turn off your kettle. If you carry out two practicals, which you did, one of them we control the amount of light falling on the LDR, and we measure the resistance, and we see that it is a steep fall off. Doesn't go to zero, looks quite familiar, decay curve. And you do the same, hot cup of water, cool it off, and we get the same kind of curve. Both are negative, non-linear coefficients. And one way of dealing with the questions that arise from that is this format. I really like this. We can take an example. In the dark, what is the current? So, as the light goes down, if we do the Thunderbirds or the Scouser impression with your hands, we can say as L goes down, the other hand goes up. And if R goes down, if R goes up, current goes down. So to answer a question like in the dark, what happens to the current, we can see there that it's going down. Pause the video, have a go at the other three. Next, Ohm's law, invented by George Ohms. He was looking at the relationship between a piece of metal, applying a push, we call it a voltage, and looking at what current, I, flows through. He discovered every metal had a different level of resistance to the flow of current. And so he simply just created it as a ratio, R is equal to V over I. If we add two resistors together, let's call them R1 and R2, then the total resistance is just the sum of their two parts, R1 and R2. I'm not going to go into parallel circuits. I don't think that's ever going to come up again. So that is Ohm's law in a nutshell. Put it in a triangle, VIR, and I trust by now you could rearrange that in your sleep. Next, defining electricity. Bit of a lie in year 8 telling you that it was the flow of electrons individually, because the charge on one electron is 1.6 times 10 to the minus 19 coulombs of charge. And actually we define electricity in coulombs. Just like I talk about you guys in classes, and that allows me to talk of just 20 classes instead of 561 as of today, we can talk about electrons in coulombs. To calculate the number, not that you will have to, you just do 1 over 10 times 10, 1.6 times 10 to the minus 19, and it gives you a figure of roughly 6 times 10 to the 18. So in 1 coulomb of charge, there are 6 million trillion electrons. That's quite a few. And we can now redefine electricity properly. We can say current is the amount of coulombs per second flowing. How many coulombs of charge pass a spot per second? And we can say voltage is the amount of energy, joules per coulomb carried. With that in mind, we can then start looking at this quantity Q, the amount of charge we have. And if we wanted to count the total amount of charge flowing, if we know I, the number of coulombs flowing per second, well then by timesing by T in seconds, that will tell us, and again we can prove it, coulombs per second times second, cancel, cancel, there is our unit of charge. It will tell you the total amount of charge that has flown in a circuit. You can whack it in a triangle, nice and easy, Q, I, T, and rearrange it as needed. And that concludes the video. There's probably a few other bits and bobs in there. It's down to you to have a look, please, and I've heard it said by people, watching the video is not enough. This is just a bonus. Alright, good luck. Bye-bye.